Now, let's go ahead and talk about thermodynamics. We had a thermochemistry unit earlier, if you remember delta H, the enthalpy, right? And I always ask students to make sure that you know how to find the delta H of the reaction, the change of the heat of reaction. So what are the 4 ways of finding delta H of the reaction? First, we have the easiest. Product minus the reactant. That's the easiest. You got a table, and we actually will have some of these similar type of calculations later on today. Do you remember what are the other ones?
There's a law.
It has this law. The one that with a bunch of equations, okay, that you have to flip or multiply some numbers. The third one is
long-awaited entropy.
So we're talking about the review of heat of reaction. So we can have calorimetry, okay, which is the MC delta T.
And bond, right?
Bond energy, yes, bond. Bonds broken minus minus bonds made. All right, so you basically just they will give you a chart with all those bond energies, and then you just assume that all the bonds are broken, and then you would assume that all the bonds that are present in the products are all new bonds. So not yet. We still have a little bit of equilibrium stuff to go over. Not much, but simple. All right, so that's delta H. So what we are about to talk about for this half of the thermodynamics unit is to talk about these 2 things, S and delta G, right, or delta S. Okay, but now. This is where I want to be very careful with the way that we phrase all these key details. Now, as we talk about H or delta H, no, actually, we would just talk about delta H. We never talk about H. There's no such thing as just the H. However, this is the change of entropy, and we do have something called S. And now, what is entropy? Disorder. If there's a word that you want to anchor this into entropy, it would be the word disorder. And what is this? Yeah. So now we have solid, liquid, and gas. Okay. So if I put a scale right here, on the vertical axis, that would be our scale for entropy. How should we draw our bar chart for solid, liquid, and gas? Yeah. So just because it's the gases are chaotic, right? The gas molecules are flying around, so therefore it is going to take there will be a lot of entropy. But then we're talking about, hey, what is the change of entropy? So for a very simple question, such as this, what if we have ice going into liquid water? What can we say about this delta S? It's going to be positive, right? Because it's getting more chaotic. Now, that's easy. But what about this? What about this? They're all gases, by the way.
It's negative because it's particle. It's no dissociation. It's like what's opposite of dissociation?
Well, I would say just 4 moles of gas going down to 2 moles of gas. So it's like 4 people going down to 2 people in the room. It's less chaotic. less disorder.
Ooh, that's a good way.
It is a good way to think about it. Okay, so it's just about how messy the room is. And for all these calculations, you will be presented a table. So basically, you just add all the products together minus the total of the reactants.
Oh, like table of values?
Just like how we do the delta H of the reaction, product minus the reactants. However, now without delta H, the unit is in kilojoules per mole. And for our delta S, well, I mean, actually the S value, it is not kilojoules. It is joules per mole K. Yes, joules per mole K. So just keep in mind that the values, the standardized value that you are given will be in joules. So you've got to do the conversion to make sure that the units are the same. If you don't write units, this will be particularly harmful. Okay?